Okay, welcome. This is our session on classes and objects. I am Dr. Paul H. Cummets. We're going to talk about some fundamentals, some foundational ideas that are enormously important. Some of the things that we're talking about today are really the bedrock of object-oriented programming, and that's basically classes and objects. I want to say in the beginning here, the good news is nothing we talk about here is terribly difficult, but you need to own this. You need to own this material. These concepts will underline pretty much everything that we do in our intermediate programming course. So here's our plan of attack. We're going to begin by comparing and contrasting some programming styles. OO, object-oriented programming, is clearly the state of the art today and has been for many years. But that was not always the case. It didn't come from nowhere. It came from actually procedural programming. So very briefly, I'll give you an example of procedural programming, show you some of the challenges, some of the difficulties that we had with procedural programming that led to the evolution and the subsequent development of object-oriented programming. So from there, we'll go into OO, and we'll talk about some powerful ideas. The ideas of objects as real-world models, and the idea that an object is an instance of a class. It's something you'll hear me and others say many, many times in discussions of object-oriented programming. And we'll finish off, and it's just a brief, just a short presentation today. We'll talk about some of the features of OO, not all of them, but some of the important features. Specifically, we'll talk a little bit about encapsulation and information hiding, two powerful ideas. So let's begin. We'll talk for a little bit this idea of procedural programming. And procedural programming was really sort of, the original programming model, if you will. Is a serial flow with some subroutines. A subroutine is a branch to another section of code where we'll perform some specific tasks, and we'll return to the point from where we branch. And the idea is, with a subroutine, you can, rather than having to insert the same code every time you want to do it, you can branch to this code section, perform your work, and come back to your serial flow. So your serial flow was task, 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 with this idea of interspersed with these subroutines. It was often iterative, a big program that would run in a big loop. I'm going to give you an example of a flight program, an aircraft flight program. It ran in a 200 millisecond loop, so it ran at 5 hertz, 5 times a second. The whole program would execute. It was often done in assembly language, Fortran, Pascal. The Pascal programming language was pretty popular for a while. The C programming language, which is still popular today. These are not the only languages, but they were some of the more prevalent languages. So let's take a look at an example near and dear to my heart. One of my first jobs out of college, I was an assembly language programmer for the U.S. Navy A-6 Intruder aircraft, a carrier-based naval aircraft. The flight program, the A-6 Intruder flight program, was a serial flow, and you can see me moving the mouse here. It began with services, things like real-time clock services, interrupt services, all your trigonometric, sines, cosines, that kinds of thing, utilities, if you will. Was followed by navigation, where we would prepare the flight instruments. It was pre-GPS, so an inertial platform. You had to get the platform straight and level before you went flying. There's also a gyroscope, a gyro compass in the airplane. We ran all the cockpit controls and displays. We did flight management, navigating the airplane from point to point on the flight plan. There was weapon selection, sensor control, running the radar and the infrared, and some ballistics calculations. This was a serial flow that ran in a big loop, 200 millisecond loop, 5 times a second, and with this idea of subroutines interspersed throughout the program. I don't mean to imply that this was a terrible model or something like that, because certainly it wasn't. A lot of very, very important work was done with this model, but it had its challenges. One of the primary challenges, these sections had a tendency to run together. So if you look here, these sections being sequential, one after another, without a real clean separation. Interdependency, dependencies between sections were created. And so, for example, the navigation section would be, partially dependent on code in the display section, or even worse, in the flight management section. The ripple effect of that, if you made changes in the flight management section, you might break something inadvertently, of course, in the navigation section. Actually, that used to happen all the time, and it was one of the challenges of this programming model. They were always under the gun errors. You make a small error and we'll get, it's hard to fix. We'll fix it later. Truth be told, it's not hugely different in the programming models of today. Because it was one big program, often referred to as spaghetti code, there was too many global variables. It was too easy to make a change in one place and break something somewhere else, and there was just not a clean delineation between these different functional areas. So it was hard to maintain, hard to come up to speed on, and hard to reuse. Again, I don't in any way, shape, or form mean to imply that it was a failed model or anything remotely like that, but it did have it had its shortcomings. So this procedural program gave rise, was the motivation for the object-oriented programming models of today. And the fundamental difference, the main difference between procedural and OO is, rather than one big section, that one big program where everything ran together, it's object-oriented program is much more of a component-based kind of idea, and those components are called objects. Now, the idea of object-oriented programming is a simple but powerful idea, and it manifests itself in the way we abstractly think about and design our software programs, as well as the actual implementation, the way we write the code. So the way, it changes the way we think about things. We talk about these components, these objects, they're real world models. We model data as real world entities. And the level of fidelity, we model with the appropriate level of fidelity for the task at hand. Funding, schedule, what is the scope that we're trying to do. So objects are real world models, and a class, so classes and objects, a class describes the data and operations of an object. Some people like to think of a class as a blueprint for objects, a blueprint of the state and behavior. So we model software components as real-world objects with state. What do objects have? Objects have state and behavior. So the state are the attributes or the data associated with an object, and the behavior or the methods or the operations. So here's an example, and we'll look at a bunch of examples here. Here's an example of a bicycle class. And this square box here that you see, this is loosely based on what's referred to as a UML, Unified Modeling Language, UML class diagram. The class name goes in the top, so this is the bicycle class. The attributes or the data goes in the middle here, and so here we have, and this is not meant to be, exhaustive or anything. There's a lot more we can say about bicycles, but for example, speed and current gear are some of the, example attributes for a bicycle. And what are some of the operations you can do with a bicycle? We can apply brakes, change gears, and of course there's lots of other things we can do. So in our model, all bicycle objects use this pattern. The pattern describes the state and the behavior. The state is identified by the attributes, and the behavior is described by the methods or the operations. We can say that objects have state, behavior, and ID. Objects have state, behavior, and ID. So building on this idea, we can say that an object is an instance of a class. The blueprint of state and behavior is called a class. So here, let's again consider our bicycle class. And we have one class, but using this blueprint, using this template, if you will, this blueprint of data, this blueprint of state and behavior, we can have instances of this blueprint, and we can model as many bicycles as we want. So here we have a bicycle called My Schwinn. My Schwinn is an object that is an instance of the bicycle class. We can also have a bicycle called, we can have an object called a Raleigh. And this is an object called a Raleigh. A Raleigh is an instance of the bicycle class. And here we have one called Your Schwinn. Your Schwinn is also an instance of the bicycle class. So here we have one bicycle, and we have many objects. So we have one class, many objects. Note that they're not identical. They may have common state and common behavior, but not every aspect need be the same. Notice that they all do have. So objects have state, behavior, and ID. They all have a different ID. And obviously they can all have different states and different behaviors. So all three of these are objects of class bicycle. Each object has similar characteristics. Each object has its own identity, state, and behavior. So we can say that this class bicycle, defines the data and behavior common to all bicycles. So let's continue. Let's really round out. Let's really embrace. Let's really embrace the model. So here are just some example classes. So here we have an aircraft class. We have a stereo class. We have a book class. So here. All of these aircraft can have, here's the state or the data flat position, heading, fuel, amount of fuel on board, airspeed, and there's obviously many other attributes that an aircraft can have. Here's some of the behavior. So here's the state, here's the behavior. A quick word before we continue. You will find interchangeably in the literature the idea of data, attributes, and state all really sort of refer to the same thing. Data, attribute, state, that's this information right here. The behavior or the methods are often referred to in the same way. Here, move flaps is behavior, change heading is behavior, extend gear is behavior. Let's look at the stereo class. Stereo can have a volume, power. Does it have a Dolby setting or not? This could be the setting from 0 to 10 on the volume control. This can be what is the power rating for this stereo? Is it 30 watts or something? And Dolby, maybe that's Boolean, maybe just true or false. Is it equipped with a Dolby noise reduction system? Here, set volume, get volume, set Dolby, or turn it on and off. It could also be, is the Dolby on or off? This is the behavior. Here's continue with the book class. The book class can have a title, an author, a number of pages, the current page, and we've got some methods here: turn page, get title, set title. So I think you get the point here. We can have many books, and the books can be very unique, just like real books. That's kind of the point. But they have many common attributes, and we can use those in our software model. We're going to create a class called book, and specific instantiations of that class are objects. And we might have, the War and Peace, the War and Peace instance of the book object, or any other book that you're reading. So classes define common characteristics. Objects realize those characteristics. So let's look at some specifics just a little bit. Let's look a little bit at behavior. And the behavior I've been referring to, and if the behavior is sort of the abstract, the methods, the idea of a method, that's an implementation artifact. That's something I'm going to use to realize, to actually write code that models the behavior of the object. So objects communicate via methods, and we pass information to objects via parameters in methods calls. Methods may or may not return information. So here's a couple of examples here. We've got public void set title string s. So what have we got going here? This is a method whose name is set title. It accepts one parameter of type string. That parameter is indicated as S in the parameter list. You can call it whatever, it could be called whatever you like. It's got public access. If you know what that means, great. More on that later. And notice here, void. Void implies that it does not return any information. Let's look down below, compare and contrast. So here is a method called getSpeed. It doesn't take any parameters, but it returns an int. So consider our bicycle class from a few slides ago. It had a speed setting. If you wanted to know the speed of a bicycle object, you would invoke this method. So what does this do? This returns, this method here is how you externally access the state of this bicycle object. If you wanted to get the speed, you would invoke this get speed method. No parameter is required, and it returns an integer. So the methods are defined in the class, and the methods may accept parameters. They may or may not return a value. Here, void, it does not return a value. Here, int, it does return a value. An example, public, here's an example method. Public double calculate, so the name of this method is calculate miles per gallon. It returns a double. It has public access. And we pass in as parameters, so you can have no parameters, or you can have a parameter list. Int, we pass in an integer, miles to travel, and a double, gallons used. So we calculate miles per gallon. A method is, so here is an example, and the point here is objects communicate via methods. So the behavior and the communication between objects is via the methods that are available in that object. A method, a special case, a method that is used by all instances of a class is called a static or a class method. You'll see this in your reading. More on this as we go, but just a quick heads up. A method is used by all instances of a class is a static or a class method. Just a couple more things here. Let's talk a little bit about some of the key, not all, but some of the key features of object orientation and object-oriented programming. Two of those features are this idea of encapsulation and this idea of information hiding. So here, what exactly is encapsulation? So note the graphic here. What the graphic is trying to show you is that the data or the state is encapsulated by the public interface available on that object. So here we've got some attributes here. The little green box is showing speed. Here, this could be the wheels are turning at 90 revolutions per minute. The little red triangle is showing that we're in 5th gear. This information is managed internally by the object. It's not publicly available. So it represents the state of the object. How do we get access? How do we get access to this state? So we provide methods to get or set the object data. There's getters and setters, or so-called accessors and mutators. So these getters and setters, this leads rise to this idea of information hiding. Information hiding is really an extension of the same idea as encapsulation. We access object data through its public interface. So we present an interface, and that interface, think about it, what is that public interface? It's the method signatures we were just looking at previously. Those method signatures describe the public information to our encapsulated, in this case, bicycle object. So we use this public interface. The implementation is hidden. What's the great advantage of this? Think back to the discussion from a few minutes ago of procedural programming, where you had these dependencies between sections, and you made sections, you made a change one place, it caused this rippling effect elsewhere. The beauty of these ideas of encapsulation and information hiding is, if for some reason we needed to change the implementation on, inside our object, in the engine, if you will. Changes in implementation would not break or ripple through to the public interface. So we can make changes, and users of our classes and objects, these changes are transparent to them. And ostensibly we made the changes to make an improvement or something, but the idea is we encapsulate, so we hide the state, if you will, of the object data, and we manage it internally, and we provide access via a public interface. The implementation is hidden. So these are simple but enormously powerful ideas. One of the things you have to think about when you're looking at some of these programming ideas, these software engineering ideas, most things, when you look at it at the level we're looking at right now, they're pretty simple. It's pretty straightforward. The real benefit is gained. Think of a modern commercial implementation. Think of a modern operating system. Millions and millions of lines of code. Think of even many commercial programs. You have the apps on your smartphone, thousands or tens of thousands of lines of code. So these simple but effective design paradigms really carry a lot of weight when you think of scale. So wrapping up here, so think of classes as blueprints for data and operations on data. The data is the attributes, behavior is methods. Objects are specific instances of a class. One class, we can have many objects. And the thing you'll hear people say, an object is an instance of a class. An object is an instance of a class. Objects communicate via methods, and you will write plenty of classes, instantiate plenty of objects, and have plenty of methods in the classes that manifest themselves in your objects in this class. Finally, we hit on a couple of the, not all, but a couple of the key points of object orientation. Encapsulation, the idea that an object's data is not immediately accessible, on this idea of information hiding. To access the state, you've got to go through the public interface. So that's all for today. More on this as we go. So thank you very much.